Okay, time to get started. So here we go. Last time we finished section 1.6, which again, sort of, oddly we covered before 1.1. Starting off now at 1.1, and by the way, we're going to go straight through for a little while. There are going to be a couple little jumps and zigs a little bit later on, but for the rest of chapter 1, in order. Okay, not much that I'm going to say about 1.1. A couple of kind of notational things. The book uses bold to distinguish vectors from scalars. I guess that works. It's just that we can't do that with handwriting very well unless you want to sit there and, every time you want to write a letter, it would just be really slow in algebra, so I think that's kind of prohibitive. So I prefer the little vector hat to bold. It's a lot easier to do. Just a quick cultural point, I will note that in a lot of more advanced textbooks, they just won't put any modifier at all, just V. And it's your job as the reader to remember that when V was defined several pages back, they said it was a vector, and you're supposed to remember that. But in introductory courses like this one, I think it's reasonable and appropriate to put the little thing over it it's easier to keep track of what's going on. Okay. All right. Second thing, the book uses a notation that I just kind of slightly bugs me. It's not wrong or anything. It's fine. But they use that notation to represent this vector. There's a couple of things that I don't care for about that. For one thing, this vector is the same exact vector as that. Let's try to draw it actually parallel here. That and this and this. That's all the same vector. And if we're going to use this to denote that vector, seems a little weird because this arrow doesn't start at P1 and it doesn't end at P2, right? So it kind of makes it look like that this notation here, could it be that that's referring just to that arrow? It's not usually the case. Usually they're talking about the vector, namely the collection of all these arrows. So the notation that makes it look like it's specific to an arrow, I think, is weird. That's just a personal preference. Now, I have a preferred alternative, and that is to recall that these points, P1, for example, don't forget there is a natural one-to-one correspondence between points and vectors. Any point, you can think of it as being a vector. Any vector, you can think of it as a point, right? And I think it's very convenient to kind of blur the distinction between points and vectors. They are different, absolutely. But if you blur the distinction, context should always make it clear which one you're talking about. And there's really no downside when you're doing math at this level. So that point P1, you can reinterpret it as being that vector P1. And this point P2, you can kind of reinterpret as being that vector P2. And then very reasonably, the green you could interpret as P2 minus P1. And that vector algebra absolutely gives you the correct vector. So between this choice, would you rather P1, P2, or would you rather P2 minus P1? Not only does my preferred choice here not seemingly refer to an arrow instead of a vector, but it also exposes the algebra. Algebra is a good thing. If there's algebra involved, I want to see it. I want to be able to use it. Right? And this notation over here kind of conceals the algebra that's actually happening in there. So anyway, this is just notation. Not a big deal. But for whatever it's worth, I'm always going to use this notation right here, and I'm basically never going to use that notation right there. Okay. All righty. How are we doing? Is everybody with me? Questions? Yes?
So what's the thing about vectors being the same?
Yeah, so they're not technically the same. So a point is a location, right? A vector is a direction and a magnitude. But so even though they're different things, they are in a natural correspondence, and that goes as follows. If you here's your XY plane, and if you have I'll do the orange. If you have a point and you ask what is the corresponding vector, the way you find the corresponding vector is to draw an arrow from the origin to that point, and well, that's the corresponding vector, right? And then likewise, if you start with the green, you have a vector. The corresponding point is identified by finding first which of the arrows has its tail at the origin, and then wherever the head of that arrow is, that's the corresponding point. So if you blur this distinction and kind of think of points as, you can think of a point as by way of its position vector and vice versa, then it just makes a lot of things easier. You don't have to have separate rules for, like for example, we have a rule for vector plus vector. Do we need a separate rule for point plus vector? Well, if we really insist on viewing them as different things, we would need a whole separate rule for what is a point plus a vector. If you blur the distinction, point plus vector is vector plus vector, it's all the same. This is very convenient. Does that make sense? Okay, yeah. All right. Okay. So, moving along. That's all I'm going to say about section 1.1. Moving on now to 1.2. Let me remind you, there is much more than that in section 1.1. It's just stuff that I think you'll find to be either review of stuff you've already seen or highly readable, and I'm just going to let you read it. So one or the other, again, you don't have to make these tough choices on how to spend the very, very limited, valuable time we have in class, and most of 1.1 doesn't really make that cut. Okay, still you have to know it, so make sure to read all of 1.1. Alrighty, 1.2. Again, a lot of stuff about vectors. Again, a lot of stuff I'm not going to talk about in class. Again, you are responsible for it. Make sure to read it. Make sure that you either refresh your memory or learn it. But I am going to talk about quite a bit of 1.2, namely parameterizations. I think a lot of students, possibly most of you, either haven't seen parameterizations before or maybe haven't seen many. Don't know as much about parameterizations as I'd like. So we're going to spend most of today talking about parameterizations. First of all, what is a parameterization? It's a function that gives position in terms of a single parameter. Position as a function of a single parameter. Now, here's the thing, though, that single parameter, we tend to use the letter T, and we tend to think of that as being time. So, with that point of view, let me restate what a parameterization is. Parameterization gives position as a function of time. And what I like about this take is position as a function of time is something we have an experience with. In fact, that's what drawing is, really, if you think about it, right? Watch me draw a curve here. I put my pen down, and now as time passes, the pen is at different positions, right? So, different positions as a function of time is literally the act of drawing. So that's why I think it's a really nice thing to use time as being your single parameter. If you make that choice, a parameterization is just a mathematical representation of the act of drawing something. Okay. All right. So here's a nice first example. Here you go. We have a couple of functions of time. Notice that this is telling us our x-coordinate as a function of time and our y-coordinate as a function of time. Thus, altogether, giving us both x and y, namely giving us our position as a function of time. So, this is what a parameterization looks like. Anybody with me? All right. Okay, next natural question. This is a parameterization. What does it draw? What is this a parameterization of? All right, now, this is a tricky question. When you have a parameterization given to you and you want to sort of infer what is it drawing, there is no single process for answering that question. There's a bunch of different tools that, depending on the circumstance, might be useful in helping you answer that question. But the proper tool for the job Depends on the particulars of the job. So I have several examples that I'm going to show you. Each one of the examples I'm going to show you, I'm going to solve with a different method. And all of the methods are things that you should know because they, again, depending on the task at hand, they might be useful. Okay. All right. So this first one. What is this thing? What is, x equals this formula? Well, keep in mind, the coordinate x is cosine t. The coordinate y is sine t. And if I were to plug that in to this equation, whoops, colors. If I were to plug that in to this equation, the equation works. Right? So, because we get cosine squared plus sine squared, which is indeed 1. And so what that means then, if you think about it, what that means is that every point generated by this parameterization, they all satisfy that equation. They are therefore all on the unit circle, which pretty strongly suggests that that parameterization is probably drawing the unit circle. And in fact, that's right. Everybody see what happened there? Now, there is a natural question to ask here, which is, where did this come from? What made me dream that up? What made me think to try plugging in x and y into that specific equation? I'm going to call it experience, but roughly speaking, the idea was I looked at and saw, okay, I've got cosine t and sine t. I need some algebra that I can plug into where cosine t and sine t are involved in the same equation. Can I think of, do I remember any equations that involve sine and cosine? And then I remember, oh yeah, Pythagorean identity, and boom, it's all over at that point. Everybody okay with that? But you can imagine, this is a very narrow technique. It only works if you kind of pre-existing already know a relationship between these formulas. And very often you don't. So sometimes this is useful, but, not always. Okay. Here's the next example. I'm going to show you 2 ways to answer this question. So, what is parameterized by this? Again, this will work sometimes, not always. Don't forget, the first formula there is x. The second one is, colors. Second one is y. What you're going to do with this technique, solve for t in the first formula, then plug that in to the second formula, and out comes, you'll notice, a relationship between x and y, which you can multiply out, blah, blah, simplify, and out comes the equation of a line. So, as a result of this little clever plugging in process, we see that parameterization parameterizes a line. Everybody see how that works? Yeah.
We solve for t, what do we equate it to? T minus 1 equals 2.
Yeah, so right, so where I started with was the fact that t minus 1 is equal to x.
Oh.
Yeah. And so that's the thing. You got to remember, when you have a parameterization, whatever the first coordinate is, that's whatever variable represents your first coordinate, typically x, right? And then, so, I guess you could write that down, x equals t minus 1, and then in that equation, you solve for t. All right. Okay. Yeah. Now, what would go wrong, right? And what about this could make this method not work? Well, what if this were a much uglier formula? What if instead of t minus 1, what if that was t to the 5th plus t to the 4th minus 17 t cubed plus 28? No, then you can't solve for t, right? And you're dead in the water before you even start. Right? So again, this method, it works sometimes, is a good tool for your toolbox, but it only works sometimes. Okay, now here's a different method that we can apply to the same question. So same parameterization. I'm not going to solve for t here. What we're going to do here, again recalling that the first the first formula gives me my x. The second formula tells me my y. What you're going to try to do is to figure out something, if you can, if it looks like it's reasonably doable, try to figure out something you can do to take this and make it turn into that. What sequence of operations can you apply that will turn the green expression of t into the blue expression of t? And now this is not hard in this case. Notice in this first step, all I did is multiply both sides by 3. And then in the second step, all I did was add 7 to both sides of the equation. And the result is that some function of x is then equal to y. Therefore, I have a algebraic relationship between x and y. Yes?
So this final equation, y equals 3x plus 7, how does that correspond to the initial vector x?
So what we have here then, this y equals 3x plus 7 is what we would call the equation of the line. This thing here is a parameterization of the line. Yeah. Does that make sense? Yeah. And the distinction between these is something I'm gonna dwell on pretty significantly near the end of the lecture. Be on the lookout for that in about half an hour. Yeah. Okay. Alrighty. Let's see a three-dimensional example. Here is a parameterization. Position is a function of time, but notice this is giving you x, y, and z, all as functions of time. And so this draws out, if you will, it draws out a curve in space. Now, a temptation would be to say, let's find the equation of that curve. But if you think about it, an equation in space typically will give you a surface, not a curve. We're going to see a lot of examples of that later on. We'll see. Anyway, later in the course, not today. So, aiming to find an equation like we did in the previous examples, not likely to work. Okay. But here's what you can do. Again, this is just tools for your toolbox. Sometimes you'll happen upon a circumstance like this one where you might notice the following convenience. Look at this right here. Cosine and sine. That looks just like the first example we saw. I feel like that looks like a circle. Now, that's not my parameterization has a third coordinate. So it's not that this is a circle. It's not. It's not a circle. But if I throw away the z coordinate, right? Just throwing away the z coordinate. In other words, geometrically said, if I look at the projection, if I look at the shadow down in the xy plane, that shadow is literally cosine t sine t. That projection to the xy plane, cosine t sine t, and I already know what that is. That's a circle, and so I know that in the xy plane, it's kind of going around in a circle like this. What do you think? Okay. Now, it doesn't answer my question. I still don't know what the curve is. Ignore the picture giving away the answer. But even though I haven't yet concluded what the curve is, I do know some pretty useful information. I know what its shadow looks like. And then I can make a kind of an analogous observation. Let's look at the third coordinate by itself. What would it mean if I were to look just at the third coordinate? Well, that's a projection to the z-axis. I'm ignoring x and y, looking only at z. That means I'm looking at a projection to the z-axis. And this, again, is a pretty easy formula. In this case, the way I understand that is not because it's something I've already dealt with, but it's just because it's easy. It's z equals t. Height increases at the same rate time does. We're going up at a constant rate, in other words. Right? So by looking at these projections, I understand what's happening in the xy plane, I understand what's happening in the z plane, and I can kind of use geometric intuition to sort of combine these together. So you got to imagine, all right, I'm looking for what what path does a point follow when its shadow is doing this and its height is increasing at a constant rate? There's really only one curve that can do that, and that's the helix that I have drawn here. So this parameterization describes that curve. Everybody okay? Yes.
Going off about what you said with like the shadow
Yeah.
in the XY plane.
Yeah.
Could you say that like the shadow in like the ZY plane is like a sinusoidal wave?
Yeah, you could. Yeah, totally. There's lots of different projections that you could think about. That's totally fine. I think that would be less it'd be less convenient than this, but absolutely, totally works. Yep. Anybody else? All right. Okay. So again, tools for the toolbox. Never know when they're going to work. All right. Now, we're going to now consider what I'm going to call the opposite question. Just to clarify what I mean by that, let me come back to this picture. As a reminder, what did we do in this question? We were given the parameterization, and then we deduced from that. We answered the question, in other words, what is the resulting curve? So if you think of diagrammatically, this example is kind of going that way. But what I mean by the opposite question now is we want to ask, suppose I'm given a curve described in some way, I don't know, it depends, right? But suppose I know some information about a curve, how would I conclude the parameterization? How do I find a parameterization of a given curve? This is what we call parametrizing a curve. Parametrizing means the act of creating a parameterization. Okay. Well, again, by hook or by crook, different methods, tools for your toolbox. I'm going to show you several. I'm going to start with my favorite one. This is called I call this anyway, the graph parameterization. This is a very powerful technique. It works in a shockingly large number of cases. In those cases where it works, it's really easy to do. So this is my favorite parameterization trick. Now again, it only works sometimes. It only works if you actually have a graph. And I'm going to say much more about graphs later on, but for the moment, let me just say a graph is where one of the variables is solved for in terms of the other. Yeah, question?
You never found the equation for the spiral?
There is no equation for the helix. So an equation in space would typically give you a surface, as it turns out. And so, yeah, we had to find a different way to understand it. We're not going to be able to write down an equation. Yeah. Does that make sense? Yeah. Okay. All right. So, this only works for graphs. You have to have one of the variables solved for, in other words. And if that's the case, here's the magic trick. The magic trick is right here. Let t be the input variable. Everything will just fall into place. It just works. Let t be the input variable. In this case, the input variable there is x. All right, now let me show you an example of this, just everything falling into place. Start with this equation here. We're going to parameterize that equation. Notice it is a graph. It's a graph because I have y equals. Y is a function, a given known function of x. We're going to follow this rule. We're going to let t be the input variable. The input variable here is x. So I'm going to let t equal to x. And I claim it's basically, we've already won the game. Because if x is equal to t, then I have no choice but then to observe that y then has to equal to t squared, and victory, we have position as a function of t. So, it always works. Neat trick. Everybody happy? So, you do have to remember the trick. The trick, again, is this right here. Let t be the input variable in the equation where one of the variables is a function of the others. All right, here's another example. Here we go. Now, you'll notice in this equation right here, it does not appear to be a graph. It's certainly not written as a graph because I have not solved in this equation for one of the variables. And if you try to solve for y, you're going to lose. Right? Because you see you have e to the y squared and y in a different term, and this is algebra, just doesn't work out. Right? So you cannot solve for y, but you can solve for x pretty easily. And there's no rule that says y has to be a function of x. They're just letters of the alphabet. Alphabetical order has no mathematical significance. Right? We can solve for x as a function of y, and following the rule then, we're going to let t be the input variable. The input variable here is y. So I'm going to let y equal to t. And, well, that means that unavoidably x has to be that. And again, victory, we have position as a function of t, aka parameterization. Everybody see how this works? Okay. All right. Now, this next one is has a lot of details in it. This one is, look, the real world tends to have a lot of details and a lot of annoying inconveniences. It's just the nature of reality. But anyway, here we go. Sometimes you can use vector algebra. Sometimes vector algebra turns an intractable problem into two not that bad problems, or possibly more than two, possibly several, depending on how the geometry works out. So here, what I'm going to do is I'm going to turn one otherwise intractable problem into two fairly doable problems. So here's the story. We've got a wheel of a given radius. It's rolling on top of the x-axis. So it's kind of rolling that way and thus going that way, right? As wheels do. And I like to think of this as being a bicycle wheel, and we have a reflector attached to the, and as I have it drawn here, attached right on the rubber of the tire. It's not, they don't typically do that, right? But anyway, just to keep the algebra convenient, we're gonna have it right on the rubber there. And y'all may have seen, I sort of assume that you have, if you ever seen someone riding a bicycle in nighttime, dark conditions, and they ride their bike near a street lamp. The street lamp will reflect off of the reflector, and that reflector does this weird thing where it makes kind of a jumpy kind of pattern like that. I don't know if y'all have seen that before. It's a very distinctive kind of jumpy little round curve, kind of like this, and then it keeps going. Okay, so our goal is to parameterize that curve. Now, you may be thinking, why don't we start with finding the equation of that curve? I'll call that step one, and then we'll go from the equation to the parameterization. And the thing is, that doesn't work. If you try to find the equation of this curve, it's crash and burn. It does not work out reasonably well. It's very hard to write down an equation. It's basically not doable. Okay. So, but we are going to be able to parameterize it by the following really clever observation. The point on this curve, right, points as they move along this curve, can always be thought of as a sum of two much simpler vectors. So in particular, there's the location of the axle. The axle is doing something pretty simple, right? Axle is just moving a straight line. That's easy. There's some details. We'll work out the details. But big picture, straight line, not that big of a problem. And then plus, we're going to need this, what I'm calling D, this difference vector, that goes from the axle up to where the reflector is. And it's tempting to say that that's a hard problem because axle to the reflector, it starts off there, and then here it's like maybe that, and then over here it's like maybe that, and then there it's there, and then over here it's like that. And it's tempting to say, look at all this weird nonsense that arrow is doing. But keep in mind, those are not vectors. Those are arrows. The arrows are doing weird stuff like that. We're not interested in the arrows. We're interested in the vector. And that vector there is exactly the same as that vector. Well, I didn't draw that well, did I? Is this exactly the same as that, which is the same as that, which is the same as that, right? The location doesn't matter. Vectors don't have locations. So if you look at the standard position vector, that is, P minus A, that, as the wheel rotates, is just going around in a circle. It's just doing this. And details, and we're going to have to figure that out. But something moving around in a circle, not scary. That's fairly tractable. So again, the big idea here is we're going to think of that orange point that we want to understand that describes an otherwise extremely complicated curve. Orange we're going to view as this being blue plus green, and blue and green are easy. Everybody see the big idea? Everything that follows is details. Okay. All right. Let's start with the blue. How do we describe that axle? There's a tricky point here that we'll get to in a second. I'm going to start with the y-coordinate. The y-coordinate's actually pretty easy. Again, axles are always exactly the same amount of distance up above the road. One radius exactly. The radius is A, so the y-coordinate's clearly A. That part's a freebie. Where it gets interesting and challenging is if we try to understand what is the x-coordinate of that axle. What is the x-coordinate? And I argue as follows. First, I argue that the x-coordinate it's the amount of road that has touched rubber. Right? And now I'm going to make the insightful appeal, which is the amount of road that has touched rubber has to equal to the amount of rubber that has touched road. Because bicycle wheels, let's assume dry roads and, good tread, etc. There's no slipping. And so the amount of rubber has to equal to the amount of road. What do you think? Everybody on board with that? This is an insight. By the way, here's a comment that I think this will be useful throughout the course. There are some tricks in math, certainly in this class, that, I never would have thought of that in a million years. But somebody showed me, and it was a really insightful little point, and oh my gosh, that one little insight, and it turns a hard problem into basically an easy problem. And I'll try to point those out as we go along and make a big deal out of it. Otherwise, here's what happened to me. I was learning math one time, and one of these things happened, and the teacher didn't explain that, okay, this is a really tricky, insightful observation. You shouldn't expect to have thought of it on your own. And I thought, wow, I never would have thought of that on my own. I guess I'm not very good at math. And I got pretty intimidated. And then I eventually realized, oh, no, he didn't dream that up either. Somebody showed him. And somebody showed that person, and somebody showed that person. And you can trace it back to, some really, really insightful, person hundreds of years ago, right? But some little tricks of the course are very tricky and not something I would expect you to think of on your own. That said, now that I've showed you this trick, that rubber equals road, now you don't have to think of it, right? You've been shown this trick, and so you can remember, you can understand the insight, remember it, and so if there is a bicycle wheel question on an exam, it's very reasonable for me to ask that you would remember that trick. Okay, does that make sense? Did everybody see the distinction there? Yes. Yeah. So if you have a wheel that's sort of rolling along the road, the idea is that if it's not slipping, right? Then as the wheel kind of goes along the road, everywhere it makes contact, the amount of rubber and the amount of road, they kind of line up there. And so grand total, the amount, let's see, let me use different colors here. The amount of road that has touched rubber just has to equal to the amount of rubber that has touched road. Does that make sense? Anything different, if these were different, then that would mean that there was some sort of slipping or dragging or, somebody's peeling out or, something like that. Yeah, skidding, effectively. So that's the whole idea there. Yeah. All right. Okay, so why does this help our problem? Well, the x-coordinate is equal to the amount of road, which is equal to the amount of rubber, and the amount of rubber is an arc of a known circle. And high school geometry tells us that the length of an arc on a circle is radius times angle, and we've got here that the radius is A, and the angle you can see here, the angle is what I've called here T, and so that amount of rubber is AT. How's it going? Everybody happy? Okay. All right. Okay, so we're halfway there. We've got a formula now for A. A is this. That's the formula for our axle as a function of time. Okay, next question. I need to understand these green arrows here. How do I understand the green arrows? Well, again, keep in mind those green arrows, I can draw them anywhere I want because I'm interested in vectors, not arrows. So I draw it in standard position. Standard position has the nice feature that the head is the point. And so if I can understand the point, then I understand the head of the arrow in standard position, which means I understand the vector. So I can understand what's going on with that vector just by understanding how that point is moving around. And the location of that point there is actually pretty easy. It's just, it's a point on a circle. I know the angle, I know the radius, and sines and cosines and all that. Colors. This angle theta, that's the usual theta from trig class, measured as usual. Theta is always measured off of the positive part of the x-axis, and that point is a cosine theta, a sine theta. Everybody okay with that? There's a little twist coming up, but yeah.
Not like a general thing, that any point circle.
Yeah, it's kind of the definition of sine and cosine. Sine and cosine are defined in terms of the unit circle, and this is just A times as big, and so we multiply the vector times A. Yeah. Right. Okay. Now, tempting to call that done, but the problem is these are now in terms of different parameters. I've got the axle in terms of T, but I have the green vector in terms of theta. Theta and T are not the same variable, and you can explicitly see that in this picture here. Theta, let's see here, I'm going to zoom in so we can see better. Theta is, theta is that angle. T, as we have it set up from before, is this angle. Clearly different, but what's convenient to be able to say is that they add up to 3/4 of a turn, aka 3 pi over 2. So if they add up to 3 pi over 2, then I can solve for theta. Theta is just 3 pi over 2 minus t. And so I can write that down over here. Let's see here. 3 pi over 2 and theta is 3 pi over 2 minus t. Plug that in for where these thetas are. And then now you do have to remember your angle addition formulas. I know a lot of y'all, it's been a while since high school trig. You may have finished your trig class and thought, oh my gosh, thank God I'll never need to know that stuff again. Sorry to report, not the case. Angle addition formulas are really useful. Don't need to worry about secant and tan and stuff like that. But the angle addition formulas for sine and cosine get used a lot. It's very important. I urge you to remind yourself and re-memorize those two angle addition formulas. And that turns this formula into this function of t. And now it's all over because, again, keep in mind the whole point was that blue plus green equals orange. Right? So blue plus green is orange. Well, there's green. And there's blue. And blue plus green is orange. And we have now parameterized that curve. We've parameterized this wacky thing there. Yes?
Could you write like the final answer as like within one instead of
Yeah, totally. Yeah, you can just add the vectors. Yep, absolutely. I left them separate, just kind of visually. It's kind of nice to be able to. But yeah, if you want to make in some sense, sort of more compact, more finalized answer, yeah, feel free. On an exam, I doubt I would care about the distinction, so you can kind of do either. But it's perfectly fine either way. Yeah. Okay. All right. So, again, lots of details, but remember what the big point here is. The big point is that vector addition, all right? Vector algebra allowed me to turn an intractable problem into two medium, not that bad problems. So that was the foot in the door. Okay, moving along. How to parameterize a line. Sometimes you are given a point on the line and a vector parallel to the line. And sometimes this is the only information you know. You don't know the equation for the line. You don't know a parameterization of the line. All you know is a point and a parallel vector. That's it. How would we parameterize from this? And a nice little trick is to strategize as follows. Well, how about we start on the line? I already know how to do that. X naught has me on the line. This other point on the line that I want to generate, I can get to simply by adding that vector, which of course is not the same as the parallel vector I was given, but even though it's not the same, it's a scalar multiple of that parallel vector I was given. So, literally then, scalar multiple of that parallel vector I was given. And altogether then, check it out, that parameterizes, that allows you to write position on the line as a function of that one parameter. I saw it coming. I chose that scalar parameter to be t, and then I've got position on the line as a function of t. Yeah?
We're treating the line as a vector.
I'm sorry, speak up just a little bit.
Are we treating the line as a vector?
I'm describing the line here by the process of how would I draw it. In other words, what would be the motion of a particle, the motion of a point that sort of traces out the line. And that point that's tracing it out, I got to give it a name, and I've chosen to call it X. Does that make sense? That's if you look back at all of our other parameterizations. Here we go. Here's our first one. X is just a shorthand for the X and Y coordinates of the points that we're tracing out with the parameterization. Is that cool? Okay. All right. Okay, let's see here. Okay, yeah. Let's see. Real quick, I'm going to take stock on where I am. Okay, yeah, I guess we're doing all right time-wise. Okay. Next example. And again, notice all the methods that I'm using to parameterize stuff here. They're all different tools applied to different circumstances, and, there is no single one that's going to always work. So filling up your toolbox with various different tools, and you have to make the right choice in the right circumstance, or, so anyway, here you go, more tools. Sometimes, what you want to parameterize, in this case an ellipse, there's the equation of ellipse. Sometimes it's a deformation of something that you already have a parameterization of. Now I'm going to remind y'all, ellipses are what you get when you stretch out a circle. Hope everybody remembers that from geometry class long ago. But that's if you take out a circle, you stretch it by some factor in the x direction, by some factor in the y direction, the result is an ellipse. So this ellipse here, even though I don't know how to parameterize it, I do know how to parameterize the circle. So I have an existing parameterization, and I'm just going to tweak it to match the very, very similar thing that I'm trying to parameterize. So the details, keep in mind, from Algebra 2, we know what that ellipse looks like, and apparently I need to stretch in the x direction by a factor of 3, and stretching by a factor of 3 in the x direction, we get by multiplying all the x coordinates by 3. So notice I'm starting with my existing parameterization of that unit circle, and what I did there is in order to do the horizontal stretching, I just multiply all the x coordinates by 3. And likewise, analogously, notice I'm going to need to stretch vertically by a factor of 2. So I can stretch vertically by a factor of 2 by literally just multiplying all the y coordinates by 2. Is that cool? So I had a parameterization of the circle, and I tweaked it to get a parameterization of the ellipse. So it's a good trick, sometimes useful. And by the way, I mean, here the tweak was stretching. It won't always be. You might want to tweak by translating, in some direction by some amount. Well, then you would add instead of multiply. Yes?
So you just, the stretching by 3 and 2, you just got that from the equation?
Yeah, just, high school algebra tells me that that this equation here is an ellipse, that, that 3 comes from the fact that that's a 3, and this 2 comes from the fact that that's a 2. That's just, I'm sweeping all the algebra 2 under the rug. Is that vaguely familiar? Yeah. Okay. Cool. Right. Yeah.
You actually just said this, just to make sure I understand. You pick the factor by which you're expanding because of what they're being divided by.
In effect, yeah. I mean, so this number 3. I mean, I don't want to rehash high school algebra, right? But that number 3 effectively is why this, what do they call it, semi-major axis or something, is 3. But that semi-major axis being 3 is why I have to stretch by a factor of 3, because the unit circle has a semi-major axis of just 1, and so it needs to be stretched 3 times. Does that make sense? Yeah. Okay. All right. Okay, so this last, okay. Real quick, I want to draw a distinction between parameterizations and equations. A lot of people kind of put parameterizations and equations into the same kind of box. They're algebra that describes a curve. Right? I mean, you can see how people would kind of think they're kind of the same thing. They're very importantly different, though, in how they, as algebra, describe a curve. So a parameterization is what I like to call a point generator, because the parameterization is a thing where you put some variable in and then out comes points. It literally makes points that are on the curve in question. Okay, that is not what an equation is. An equation, typically, in the way equations are typically used, is what I like to call a point tester. If you have an equation, like you have some equation involving x and y, what you do with that is you take some point, you plug the point into the equation. If you have an x and a y, that goes into the equation, and what comes out is either a yes or a no. The equation either is true, the two sides are equal, in which case yes, that point is on the curve, or the equation fails. The two sides are not equal, that point is not on the curve. Okay, so for parameterizations, the points are the outputs. For equations, the points are the inputs. And that allows us a real clever approach to solving this next example that we are not going to finish in the next 16 seconds. So I'm going to go ahead and draw the line right here for today, and we'll end it there. And hope you all have a great weekend. And okay, see y'all on Monday. Oh, no, I won't see you Monday. Monday's a holiday, and so I'll see y'all Wednesday. All right, have a good one. Yeah.